Hi, this is Greg Ballard. I'm going to be talking about the arson chapter, chapter 10, and explosives, chapter 16. I teach the Forensic 105 during the fall and spring semesters. So we'll get started here on arson. This is chapter 10 in your book, Gerard, on page 245. And I combined them because arson and explosives are intimately related. So we move on into chapter 16, which is page 415 during the presentation. Well, I'll start out with hell and brimstone. Going back to ancient times, the term brimstone referred to sulfur, and the thing about sulfur is it was a yellow material, and when it would melt it was sticky and it burns. So it was something not a friendly flesh. If it got on you, it was like having molasses, and it would be burning, and it would be hell. So then there was other things that would burn that interest the ancients. Cinnabar, mercuric sulfide, was a rock, and it would burn, and as it would burn it would change into mercury, and then there would be a chemical reaction which would basically change it back into mercuric sulfide or cinnabar again, and so it seemed to be eternal. And it was also unique that it was a rock that would burn. Now, we're going to be talking about arson, and arson is setting fires to things, so we got to talk about what fire is. And before we get to fire, we'll talk about oxidation. Oxidation is a reaction of a substance or chemical with oxygen to form a new product. Methane, CH4 plus oxygen, will give you carbon dioxide plus water. Methane is very common in the swamps. It's a swamp gas. It can be found at the landfill. That's why they don't want you smoking there. And that is oxidation, combination with oxygen. Now, another oxidation reaction is taking iron with oxygen, and you get rust, Fe2O3. So iron from like a nail plus air, and you get rust. This is oxidation. Combustion. Combustion is simply oxidation reaction releasing energy. I'll go back to that methane, because if you take methane plus oxygen, you get carbon dioxide plus water plus heat and a lot of light. And it burns. If it's contained, it can explode. If it's in a large area, it can burn. Methane is the fuel that is in your gas barbecue. If you live in an apartment complex and you have piped in gas, or at home and you have piped in gas, methane is what is burning in that barbecue. And we have the love triangle. No, make that the fire triangle. You need three things to have fire: fuel, oxygen, and heat. And I kind of think of the Johnny Cash song, Down, Down, Down the Ring of Fire. But we actually have, it's a triangle of fire, not a ring of fire. And if you click on the hyperlink there, the Ring of Fire, and you will get Johnny Cash's song. Well, let's look at a campfire. A campfire gives us a pretty good example of the the triangle of fire. You will have in your campfire, you're going to have an area where you have fuel, which is the wood. And you will have a section called the pyrolysis zone. Pyrolysis is the heating of the solid fuel to produce a vapor. and that vapor is found in the decomposition region, and then oxygen from outside mixes with that vapor from the pyrolyzed wood, and that is what the flame is, the fire, and it releases radiant heat. And then also it has a convective plume. It's hot, so you have air rushing from the bottom and combine with oxygen and go on up and produce a fire. Now, fires don't just happen. You need to have a boost. X plus Y may not happen. You need X plus Y and a little energy to get a combination X, Y, and a lot of energy. The lot of energy is called the heat of combustion. And I have here that a cigarette could be an initiator, sparks from a spark or lightning, and a match. They all provide a little bit of energy to start the reaction going, and once that reaction goes, then it continues. Now, heat of combustion just gives you an idea of comparing the different fuels. For instance, if you're cold, wood, a pound of wood would give you 7,500 units of heat. I'll get to BTU in just a second, but it's a unit of heat. Well, if you had coal, just 1 pound of coal almost doubles the amount of heat. That's why coal's a pretty good thing in cold country. But you know that a lot of people have oil heaters up in the Northeast, because 1 pound of oil gives you 19,650 thermal units. And that is the British thermal unit. Okay, another comparison of heats. A candle burning. You put your hand over it and you know that it's going to burn you. That's because it's 2,250 degrees Fahrenheit. Let's go to your gas barbecue there. Methane and air gives a temperature of about 1832 Fahrenheit. That can cook your burgers. If you take methane and oxygen, it boosts that up to 2,915 Fahrenheit. Oxygen plus hydrogen, 4,532 degrees Fahrenheit. The Hindenburg fire, when the blimp, the Hindenburg, burned up, it used hydrogen, which was lighter than air, to lift the airship, and when that caught fire, it was a tremendously hot fire. C2H2, acetylene plus oxygen, gives you a temperature of 5,432 degrees Fahrenheit, which can melt metal. So that's an idea about the different temperatures you get from different fuels. What burns? Does a solid burn? Usually no. The exceptions are cinnabar, like the mercuric sulfide, and pyrophoric substances that we'll get to later, but generally solids do not burn. Now, wood's a solid, you're going to say, but it burns. But there is a process to change the wood into a gas, and that's called pyrolysis. What burns? Do liquids burn? No, liquid does not burn. But you're going to say, gas burns. Yes, because liquid with enough heat can change into a gas. And I'm talking about a gas vapor, not gasoline. But gasoline's a good example. You have gasoline on the ground. You can see the vapors coming up from it. It is those vapors that can combine with oxygen and oxidize and combust. So it is the vapors that burn. A BTU was the British thermal unit. It's just a way of measuring heat. It's the amount of heat it takes to heat up 1 pound of water 1 degree Fahrenheit, or 1 pint up to 1 degree Fahrenheit. Okay, chemical reactions. If I say a chemical reaction is exothermic, that means that it gives off heat. So if I put two chemicals together, and they release heat. That is an exothermic reaction. Methane burning is exothermic. Wood burning is exothermic. A reaction that is not a combustion would be to take calcium chloride plus water, and you get heat, and that's commonly done in the little sports first aid packages. It will have solid calcium chloride powder, and it'll have a vial of water in it that when you crush the tube, it releases the water into it, and the pack heats up, and then you can put it on those sore muscles. Endothermic is a reaction that absorbs heat, like the instant cold pack. Ammonium nitrate plus water, and you get cold, and so you can put that on that sore ankle. Now, I mentioned that a liquid will change into a vapor, and liquids will give off sufficient vapor to burn, and that's what the flash point is. Gasoline, the ignition temperature is 495 degrees Fahrenheit. If I have a pool of gasoline and I increase the temperature past 495 Fahrenheit, it can burst into flames. It'll ignite at that temperature. Now, the flash point is the temperature at which it has enough energy to produce sufficient vapor to burn. It still needs a source, an ignition source, but it does produce the significant vapor. Look, that's minus 50 for gasoline. No problem in Arizona, but take Fairbanks, Alaska in the winter time, or it could be 70 below. It may take considerable more ignition to get that to go, because it's not putting off a lot of vapor. And then you have to have a mixture, the proper mixture, a fuel-air mix. Okay? If I have vapor forming from gasoline, now you all see that every day you fill up your gas tank. You put the nozzle in the gas tank, and if you look along the side of the car, you will see a vapor there. It's a disturbance in the light, and you can see the vapor, and it falls down because it's heavier. Now, where that vapor is immediately coming out of the tank, it's very high in vapor pressure, and the fuel mixture there is kind of too high to ignite. Okay, and then away from it, there's not enough gas vapor to light. But somewhere in between that nozzle and the ground someplace, there is a point in when it's just right, and that's called the flammable range. For gasoline, it just has to be 1.3 to 6% gasoline vapor, and then it can go. And it can ignite, and that has happened many times. So the fuel-air mix is important. You have an upper explosive limit, which is the 6% for gasoline. You get beyond that, then it doesn't want to go. It's not going to react properly. Now, a fuel-air bomb is quite unique and scary. If I were to take a balloon full of gasoline and blow it up, just mechanically, it would spread out, and then if I ignited that, it's going to have an explosion, but there's a lot of fuel that's there too, and air will rush back in to that unburned fuel, and it will blow up, and you've got a whoosh and a subsequent fire that's very destructive. And if you hit the thermobaric, you should see this.
Now, one of the most devastating mixtures ever devised, the fuel-air explosive. Our next willing victim is just 10 yards away from the charge.
This jar is going to be filled with a flammable liquid, not an explosive in its own right. And in the center of this is a high explosive burster. When that detonates, it's going to throw out the liquid into a big cloud. And the cloud will then cover this charge, which is going to go off sometime after the burster, when the cloud has actually covered the charge. The results are spectacular. At 20 times atmospheric pressure, the mannequin is completely destroyed. Typical blast damage, that has absolutely seen the pressure, the crushing effect of the blast blade. Just ripped it apart. Although the fuel air explosive is incredibly powerful, it needs a lot of air to ignite properly. So it's useless in areas like...
So how'd you like the thermobaric bomb? Now that can occur in other situations. For instance, your propane barbecue. Propane has a lower explosive limit of 2.1% and an upper explosive limit of nearly 10%. Somewhere, if a gas is leaking out of here, right near the gas tank, it's too high of a propane mixture to burn or ignite. And over here, it is too low, but somewhere it can find the proper mixture, and if there happens to be an ignition source in there, boom, it goes up. Usually, unfortunate accident, not arson. Check for leaks on your barbecue. Fuel air mix, again, the flash point of gasoline, the auto ignition, the upper and lower explosives. Very commonly in Arizona is have a fuel air tragedy. It's cleaning car parts or gasoline in a garage. The vapors fill the garage and come down the driveway and find an ignition source and go back up in and blow up in the garage, causing a fire. And unfortunately there are deaths, and we investigate and find out it just turned out to be an accident, although a rather tragic and unfortunate accident. Now, there's different types of combustion. We have glowing combustion. For instance, a cigarette. The cherry on a cigarette, the glowing end of a cigarette, is called glowing combustion. And the cigarette companies go through great lengths to make sure that that will be an even burn. You don't have a cigarette that's on fire. It wouldn't be as steady for the smokers. And so it has a ability to burn slow enough that it will not be a problem. Now, something new in cigarettes is the fire-safe cigarettes, and they actually have bands in the cigarette that slow down that burn, so that if the cigarette is not inhaled on, it may actually go out, and that's for fire safety in the house. Campfires are another example of glowing combustion, and I have hyperlinks in there. Basically, we all know that a campfire not put out correctly, those coals, even when buried, can be glowing. They can have glowing combustion, and if a wind blows by, then it is heated up enough that it can start a fire again, very commonly known as a forest fire. Spontaneous combustion. This is the thing of late night George Norrie type things. Many people think that people spontaneously burst into flames, and forensically speaking, in the research, that has not been found to happen. Most commonly, it is where somebody has fallen asleep with a cigarette, and the cigarette falls onto their clothing or bedding material, and it ignites the skin, the fat in the skin, And everybody that has cooked chicken on the barbecue knows that if you have the skin on there and the fat, that can start and burn at a furious rate. Now, humans don't spontaneously combust. There are two things that we know that do spontaneously combust: hay and linseed oil. Both of those occur due to bacterial action. We talked about an initiator before for the reaction. We talked about a match. We talked about having a spark. Well, bacteria can do it too. And in hay, there can be an area where bacteria are eating on the inside of the hay, a moist area. It warms up and warms up and warms up, and then a breeze can come through, and that can start a reaction where the fire will go and you have a big barn fire. Linseed oil is used on brand new wood flooring to treat it, to waterproof it. And if you take the rags from the linseed oil and you leave them in a bundle, the same type bacterial action can cause that to burst into flames, and that is spontaneous combustion. That could be a incendiary device, although not very effective for percentage of time going off. Pyrophoric materials. Pyrophoric are materials that will burn on their own. They can spontaneously combust. Fine metal dust, trimethyl aluminum. That's scary stuff, and it's used in industry. It goes through town in trucks. If trimethyl aluminum catches on fire, you can't put it out. You just have to wait it out. White phosphorus. Sodium will spontaneously combust in air. Butyllithium, lithium hydride, barium, mish metal, which is flints. These are all metals and chemicals that can spontaneously combust and create quite a problem when they do. We're coming up. This is summer class, and we do have the forest fire season now. And why is there a difference between night and day on forest fires? You always see the press out at night talking about how the forest fire is slowed down and that firefighters may have an advantage to catch up during the night. Well, the difference is because an 18-degree Fahrenheit difference can change the reaction 2 to 3 times. So if it's 90 in the day in Prescott, and then it drops down to 70 at night, okay, the fire can be 2 to 3 times less fast. And so that is why it is easier to contain the fire at night. And another thing that helps in there is moisture, like in the California fires where you get moisture moving in from the sea. It slows down the reaction. Well, now, I've talked about fire a little bit. In criminal activity, people use fire to burn down things. They might try to burn a body. They might try to burn a building for insurance purposes. And our job is to detect if a fire was a natural fire, an accidental fire, or a fire set on purpose. Now, I could set a fire just crumbling up paper and lighting it and leaving, and that may effectively do the job. It may start a fire. Most often, though, people will employ something called an accelerant, which is basically a flammable substance. Then the building will burn up. And how on the earth do we detect that? Well, we use a 4-legged sensor known as a dog. A dog is used for detection at a scene for collection. And then the lab has to do the analysis. And if you click on these hyperlinks, you'll see that for legal purposes, is spelled out. that the confirmation has to be done of a dog sensing a solvent. It has to be verified by a laboratory. And those are the two steps in the process of arson investigation using a dog. So the National Fire Protection Association says any canine alert not confirmed by laboratory analysis should not be considered validated. If the dog alerts on a specific spot, the investigators know there is a better chance that the laboratory analysis will reveal the presence of an accelerant. But without laboratory collaboration, the canine alert is questionable, especially in court. Now, a canine finds a spot, thinks gasoline is there. At the crime scene, that material is collected. That material may consist of a carpet sample. It may consist of cement under the carpet that is jackhammered up, and it is put into a suitable container, and then we are going to analyzing it, use a gas chromatograph similar to this. It has a tray with samples in it, and it has an injector needle that will inject a sample into this gas chromatograph, and it will analyze the organic chemicals to see if there is an accelerant present. So an accelerant is a material intentionally placed at a scene to start and sustain a fire. For example, wood, paper, flares, gasoline, propane, lighter fluid, just butane, charcoal lighter fluid, kerosene, paint thinner, toluene, xylenes, lamp oils, turpentine, isopropyl alcohol, camp stove fuel, etc., etc., etc. Anything that burns, you could go to the aisle in Home Depot and get lots of things that will burn, can be used as an accelerant to start a fire. Now, for instance, if I have an easy chair sitting in a room, just sitting in the room, nothing's going to happen. Okay, somebody drops a cigarette in the easy chair. Okay, that may smolder for hours, and then it may start to burn. The material in the chair will start to burn. It may reach a curtain, which will start to burn. The hot gases will go up to the ceiling and pyrolyze materials in the ceiling, and it'll all start to burn, and that may all happen. Or it could go out. But what if I pour gasoline in that room around that chair and light it? Now I've created an intense fire, superheated everything. That means more material is going to pyrolyze and less chance that that'll go out. And that's what an accelerant does. So you got to light it to get it to go off. So you need an incendiary device. That could be a road flare, a candle, a match, a cigarette, a hypergolic. We'll get to that in a little bit. A Molotov cocktail, that's gasoline with a rag coming out of the bottle, and you light that and put it in the room and run away. Heated vegetable oil. Has anybody heard of the turkey basting at Thanksgiving time? This has been an accidental incendiary device. People put the turkey in the very hot oil. It's not attended to, and the oil boils over and spills on the flame, and not normally a big flammable thing like gasoline, but now it's superheated and it burns good, and it's burned down houses. Now, how do we detect that? Those things can be detected with chemical analysis and using the stereoscopic microscope to find evidence of, like the Molotov cocktail, the rag, the bottle, the match. So match pieces are left over after an incendiary device has been left. Know-how. Well, how do you get the know-how to do this? Well, if you watch this video on YouTube, they test out several incendiary devices that are found in the anarchist cookbook. And warning, like the guy says in the video, it's not smart to try this. Matter of fact, he gets a little bit stronger. He says, you're an idiot if you try it. I am just showing you or demonstrating that the internet is a resource for terrorists, criminals, and potential ER patients. Also, please note that the video in this is extremely impolite language. But it does point out that there is a lot of resource on the internet to find out how to start a fire or explosives. Now, the can. When we collect that carpet sample or that jackhammered cement sample, we put it in these clean, empty paint cans. It's shiny on the inside. It's got a lid. You put the material inside of it, you put the lid on top of it, you tap it down with a hammer. And it will keep a sample for a long time. The seal is very good on them. And then we have the ability to simply punch a hole in the top of that low-tech, put a syringe in there, suck out the vapor that's in there, put a piece of tape over the hole, and then we inject that vapor into a gas chromatograph. That's called headspace analysis. And it was a common analysis I did for years, headspace analysis. We have a whole bunch of things available to us now. When we do the headspace analysis, we put the can in the oven that produces more vapor, so it's called heated headspace. You'll find more details on page 260 in your book. There's passive headspace diffusion, where we will use a carbon material, activated charcoal, hanging in the can, and the material will get on, the vapors will be absorbed into that carbon activated charcoal, and then we can take that and put it into a test tube with another solvent and analyze that. That's also on page 260. There's what's called solid phase micro extraction. There's steam distillation, solvent extraction, and dynamic headspace purge and trap elution. All of these are different methods that different labs may use for extracting the vapors to put into the gas chromatograph mass spectrometer. This is the device that will analyze it. The gas chromatograph separates out organic chemicals based upon their chemical properties, and the mass spectra makes a fingerprint of that chemical based upon the mass particles, the weight, the size of the particles that come out. And in the end, we get an analysis that we will call an ASTM class 2, which is 4 to 12 carbons in length, and we call that gasoline. If I just simply filled out a report saying that was ASTM class 2 solvent, no jury would understand it. So generally in the reports we'll say very technically at first that it was analyzed by gas chromatography mass spectroscopy. It was found to be an ASTM class 2 solvent containing 4 to 12 carbon chains, and typically that would be of a material such as gasoline to fuel a car, and that's how it is expressed. Now, another thing that we have to be concerned about when we're doing arson analysis is pyrolysis products. And these are breakdown products of solids by heat. And for instance, if I just took a piece of carpet and put it into an oven and brought it up to 400 plus degrees, it's plastic. It's going to start to give off gaseous products. It would stink if you could smell it. Eventually those gaseous products would burn. Air cabin fires. On an airplane, that's the most devastating thing about a fire on a commercial jetliner. All those plastic cabinets and stuff burn, and the pyrolysis product there is CN. Yes, CN gas is going to kill you. Cyanide is CN gas. And that's what kills most people on a cabin fire in an airplane. It's a pyrolysis product. Also, it's a problem for post-arson exposure. For several days after the fire, people could be breathing that in. We have to collect something called a substrate control or a matrix control. And simply what that is, if I have an area of carpet that the dog has hit on where he thinks there's a solvent, I collect that. I also collect an unstained area next to the stained area. And then I may collect another area of the same type of carpet that's not heated, not charcoaled. It is just in the area. And that's what I'm going to use for the matrix controls. Because what I will do, I will heat those up in a can similar to the sample, and I will take the gas from that, I'll inject it into the gas chromatograph, and I'm going to get peaks produced by that. And those peaks are false peaks for the accelerant, and they have to be subtracted so that I am not seeing burned carpet and thinking that it's gasoline. So that is why we take a matrix control or several controls from a fire scene. Now, other difficulties with arson analysis. Solvent weathering. Has anybody left gas in a gas can for a long time, especially in Arizona? Age and heat degrade the gasoline. So I don't know if fresh gasoline will have a slightly different chart than old gasoline. There are other things like seasonal gasoline additives. There's ethanol, there's MTBE, there's ETBE, and there's TAME. These are all things that you'll see listed on the gas pump that are put in at different seasons. How about proprietary gasoline additives? Like Shell's nitrogen. There's methanol, there's detergents, and there's octane boosters. These are all different things that might be found in gasoline that I will have to explain. But here's one that's not CSI. We cannot tell that the gas came from the Chevron station at Chaparral and the 101 versus the Shell station on Indian Bend Road and the 101 like they do on CSI. I'll just go back to that ASTM class 2, 4 to 12 carbons, and consistent with the commercial product of gasoline. We cannot tell the difference between different gas stations. We can tell the difference between gasoline, kerosene, Wizard charcoal lighter, but not between gasoline at two different stations. It's just not that sensitive. So fire investigators, that's a whole different realm than generally the crime lab. That is in the realm of the fire department. Then they look at things like burn patterns, burn pattern geometry, materials, how did they react, plastics melt, wood chars, metals, did metals melt, charring of carpet, was there a container found there, how about the odors that were present. These are things that the fire investigators look at and they write up a report. The crime laboratory determines if an accelerant was present and what it was, and the fire investigator looks at the burn patterns and the essence of fire. Danger, danger. Arson crime scenes present a respiratory and chemical risk for several days post-fire. A self-contained breathing apparatus is recommended. And I have a link to the paper, but generally things like cyanides and formaldehydes can be found for days, wafting around, the fumes wafting around in a fire scene. And if you're there investigating, trying to collect samples, it could present a danger to you. And these are dangers that would be long-term, so that somebody, retiring and they come down with some type of disease. So now we're looking at it differently, and we're using protection in fire scenes, respiratory protection. Another type of arson is, well, cremation. Now, there is proper cremation, which is done professionally. It's done in a gas oven at 1400 to 2100 degrees Fahrenheit and a consistent high temperature for a consistent 2 to 3 hours. And things are reduced to ash. Now, bones will be present, but they can be easily crushed into ash. Now, amateur and ritual cremations. Well, a lot of times we'll have a case where somebody will pour gasoline over a body, light it, and run, leave, and they think that that body is going to go look like a professional cremation. And it doesn't. Sometimes they're even able to get DNA from the deep bones, like the hip bones, because there's incomplete burning. It might be 570 degrees Fahrenheit to 1650 Fahrenheit, maybe even fluxing up to 2280, but it's unsustained and it's inconsistent, and that is typical of homicide and ritual cremations. And if you click on the ritual there, you will see a YouTube video of ritual cremation in India. And I think we'll stop at this point before we get into explosives. Thank you.